Open Cluster AI Station is a high-performance distributed AI computation platform designed to scale real workloads across multiple machines. In this project, I'm building a shard-based matrix processing system that lets you distribute inference and heavy compute tasks across a cluster using zero-MQ networking and flexible backend support. Whether you're working with CPUs, GPUs, or hybrid acceleration like Vulkan or BLAS, this system is built to push performance further while staying fully open source. In this video, I'm going to walk you through how it works, what makes it different, and how you can use it yourself. This machine runs an Intel Core i7-8700, a 6-core 12-thread processor with a boost clock up to 4.6 GHz. This machine runs an Intel Core i5-6500, a 4-core 4-thread processor with boost up to 3.6 GHz and 6 MB of L3 cache. This system uses an AMD Ryzen 3 3250U, a 2-core 4-thread mobile processor with boost up to 2.6 GHz. It includes 4 MB of L3 cache and integrated Radeon graphics. I'm also running 3 legacy machines that are over 10 years old, each with 8 GB of DDR3 RAM and SSD storage. One of them uses an AMD A6 3410MX. To get started, go to the GitHub link in the description and download or clone the repository. Once it's on your system, open a terminal and cd into the project folder. From there, simply run install.sh. The installer gives you 2 options. Option 1 sets up the Python frontend for the head node. This will automatically create the Python environment, install all required dependencies, and prepare everything you need to run the GUI control interface. Option 2 installs the C++ backend for worker nodes. The script will install all necessary apt packages, download libtorch, configure the build environment, and compile the C++ distributed compute backend for you. The goal is to make the entire setup process automated, so you don't have to manually chase dependencies or configure anything yourself. After installation, the C++ backend requires a wired Ethernet connection. Make sure all machines are physically connected to the same switch or router, then configure them so they are on the same subnet. You can do this by assigning each machine an IP address on the same network range, using sudo ifconfig interface :IP address netmask 255.255.255.0. Once all your backend nodes are set up and running on the same Ethernet network, you can start the head node interface by running python/download/path opencluster AI station beta main GUI openclusterui.py. This will launch the Python frontend, initialize the cluster controller, and automatically open the GUI in your web browser. I'm currently running the TinyLlama 1.1b Chat v1.0 model across a 3-node cluster. For this test benchmark, I'm allocating 50% of the workload to node 1, 45% to node 2, and a tiny 0.05% to the laptop, just to test distributed execution. Most of the model, about 95%, is still running on node 1, but node 2 contributes using its GPUs, an AMD RX 5500 and an AMD RX 4600, which don't have CUDA cores, so all computation is CPU/GPU compatible, but not CUDA accelerated. The small portion on the laptop GPU barely contributes, but it demonstrates the cluster's ability to split workloads across heterogeneous hardware. With this setup, I'm getting roughly 1 token every 10 seconds, which makes it more of a proof of concept and benchmarking run rather than a fully optimized inference session. This isn't a great speed, but even on EXO with the same TinyLlama 1.1b Chat v1.0 model, it would still take around 45 seconds per token with the same hardware. Just for fun, I added another node, the old 4-core desktop, to the cluster with the same TinyLlama 1.1b Chat v1.0 model. Now it takes about 20 seconds per token, since I allocated 25% of the model to the slower 4-core CPU desktop. It's not faster overall, but it's a neat demonstration of how the cluster can spread workloads even across older, slower hardware. Next, I tested the Llama 3.2 3D instruct model across the cluster. I split it like this: 25% on Node 1 GPU RX 5500, 20% on Node 1 GPU RX 6400, and 5% on the 6-core 6-thread CPU of the head node. Then 20% on the laptop GPU and 5% on the laptop CPU. And finally, 25% on the 4-core desktop CPU. This demonstrates how you can distribute the model depending on your goals, whether you want faster generation or lower RAM usage. For maximum speed, you'd put more of the model on the head node's GPUs. But to save RAM, I split half of the model on the head node and distributed the other half across the other nodes. Now I'm testing the 7B model. To balance performance without running out of RAM, I can only fit about 60 to 75% of the model on the head node. My PC cannot run this model on its own. I tried it and it triggered an OOM kill when running a single node test on XO. With the cluster, I can run it, but on XO it's much slower because it cannot use my head node GPUs, RX 5500 and RX 6400, and must run entirely on CPU. This highlights the benefit of distributed heterogeneous hardware for large models. And that's where we're going to wrap it up for this video. We tested everything from small models up through 7B on a fully distributed mixed hardware cluster. Next video, we're stepping it up. I'll be downloading and testing 13B to 30B models, pushing the cluster even harder. Thank you for watching. Fuck you.